In 1986, no mobile crane on Earth could lift 1,000 tons and still legally travel a public road. The weight would destroy the surface beneath it. That single constraint held back power plants, refineries, entire industries. Then one German engineering team bet everything on a radical chassis design, shattered that ceiling, and ignited a race to 2,000 tons. A race that is now deciding who gets to build the energy grid of the future. Gottwald's engineers faced a paradox. To lift 1,000 tons, a crane needed to be massive, but every extra ton threatened to break the roads it had to travel. The answer came in the form of a 10-axle chassis, what they called a rolling bridge. Each axle, mounted on its own hydraulic suspension, spread the crane's enormous weight across 30 meters of steel and rubber. The math was relentless. No axle could bear more than 40 tons if the machine was to move legally across Europe's highways. Every calculation, every weld, every bolt had to serve that single goal: mobility without compromise. The AMK 1000's frame was more than a skeleton. It was a living system, adjusting itself to the road's surface in real time. Early digital controls, rare for the era, monitored tilt, load, and boom angle, shutting down the lift the moment any number edged toward danger. As one Gottwald engineer put it, "We didn't just build a crane, we built a moving bridge with a brain." In March 1986, this theory met reality on the docks of Rotterdam. The AMK 1000 lifted a 900-ton offshore platform section in a single continuous operation. No extra counterweight, no multi-day assembly, no road damage. The axle load stayed under 40 tons, and the ground pressure never exceeded 0.3 megapascals. Permit inspectors watched telemetry in real time, confirming that the rolling bridge concept worked not just on paper, but on the unforgiving concrete of Europe's busiest port. The AMK 1000 had done what no mobile crane before it could: deliver extreme lifting power and cross a continent under its own strength. The rules of the game had changed. Every contender in the global crane race is measured by a single, unforgiving yardstick. How much weight can it move, and how fast can it do it under real-world constraints? The answer is captured in a deceptively simple formula: ton-hours per hour. This metric multiplies the mass lifted by the time it is held aloft, then divides by the total time from first setup to final placement. It is not just about brute strength. A machine that can hoist 1,000 tons but takes 3 days to assemble and move scores lower than a smaller crane that completes its job in a single shift. The real champions are those that combine massive lifting power with relentless efficiency. Take the AMK 1000's Rotterdam lift, 900 tons raised in a single continuous operation, with the entire cycle, setup, lift, and repositioning, completed in under 36 hours. That is a score of 25 ton-hours per hour, a figure that dwarfed the multi-day, multi-trailer operations of the previous decade. Later machines would push this number even higher, not just by increasing capacity, but by slashing setup and travel times with modular booms, self-erecting frames, and computer-controlled hydraulics. This is the race's true metric, a contest of throughput, not just peak numbers. It is a measure that exposes every weakness in a design, from cumbersome road permits to slow assembly, and rewards only those breakthroughs that turn raw muscle into usable, repeatable work. In the world of ultra-heavy lifting, the stopwatch is as important as the scale. And as the stakes rise, from offshore wind farms to high-speed rail, every hour saved means millions earned, and a step closer to building the infrastructure of the future. Wind is the enemy of height. At altitudes above 100 meters, even a modest gust can twist a crane boom into a vibrating blade, threatening both the load and the machine itself. For years, the only answer was brute counterweight. Stack more steel, widen the stance, accept the limits. But in the early 1990s, Demog's engineers took a different approach. They asked, what if stability could be engineered sideways, not just down? The result was the sideways Superlift on the AC-1000, a breakthrough in lateral stabilization. Instead of relying solely on mass, the crane used a pair of hydraulic arms that extended perpendicular to the boom, anchoring to massive outrigger pads. These arms did not just resist tipping, they generated a counter moment, pushing back against the boom's tendency to sway under wind load. Dr. Andreas Bohm, lead engineer on the project, described it as turning the crane into a lever, not just a pillar. Force diagrams from the original field test show the effect. As the boom rises past 80 meters, the sideways Superlift redistributes load from the base to the extended outriggers, flattening the curve of lateral deflection. In a 1994 test at the Husum wind site, the AC-1000 hoisted a 56-ton turbine nacelle to 120 meters in sustained crosswinds, a record at the time. Sensors recorded less than 2 centimeters of lateral tip at full extension, where older designs would have flexed 5 times as much or been forced to abort. This geometry did not just beat the wind, it made possible a new class of lifts. Now, turbine nacelles and bridge modules could be placed at heights and angles that once required stationary gantries or multiple cranes. The sideways Superlift proved that with the right mechanics, vertical ambition did not have to mean risk. Liebherr's LTM 1200 9.1 does not roll onto a job site as a single behemoth. It arrives as a fleet, 5 separate vehicles, each loaded with a piece of the machine. The heart of the operation is its modular boom, 4 telescopic sections, each nearly 28 meters long, engineered to lock together with millimeter precision. The convoy itself weighs in at around 1,200 tons, but no single truck exceeds the strict 250-ton per axle highway limit. Assembly plays out like a choreographed sequence. The chassis is positioned first and anchored on prepared ground. A mobile crane, small by comparison, lifts the first boom module onto the frame. One by one, the remaining sections are slotted in, dovetail joints and hydraulic latches snapping them into a single rigid spine. Each connection is checked by hand and by computer, every bolt torqued to spec. Counterweight arrives last. Modular tanks filled with water or concrete on site are hoisted into place. Within 3 hours, the entire system is balanced and ready for self-diagnostics. Liebherr's field lead, Thomas Muller, describes the process as building a bridge upward, not across, where every hour shaved from assembly means a project delivered ahead of schedule. The stopwatch is relentless. Under optimal conditions, the full assembly, chassis, boom, ballast, and final hydraulic checks clocks in at 7 hours and 45 minutes. No special road permits for the assembled crane are needed because nothing this massive ever moves as a single unit. The trade-off is clear. It means more time in the field and total freedom from the old road restrictions that once held the industry back. In the logistics race, modularity is the new muscle. Mud, ruts, and unpredictable slopes once spelled disaster for even the world's most powerful cranes. XCMG's XCA600 answers with a system that senses, thinks, and adapts on the move. At the heart of its 12-axle chassis, independent steering actuators and a network of load sensors scan the ground beneath each tire, recalculating balance hundreds of times per second. The result is a turning radius under 18 meters, even with a full counterweight, and the ability to crawl across gradients that would sideline lesser machines. Dynamic suspension keeps every axle planted, redistributing force as the terrain shifts. ECTs. According to XME's lead demo engineer, the crane feels the ground before it rolls, adjusting its boom geometry and leveling stance in real time. What used to require days of site prep and grading now happens through code and hydraulics, pushing the frontier of heavy lifting beyond the edge of the pavement. 12 axles stretch across the length of a city block, each one engineered to share the load of a 2,000-ton giant. In the world of heavy lifting, the Zoomlion QAY 2000 Convoy is less a vehicle than a moving ecosystem. Diesel generators, hydraulic power stations, and modular counterweight tanks, all synchronized by a convoy manager whose job is part engineer, part air traffic controller. Every move begins months before the crane itself rolls out. Permit officials pore over route maps, calculating bridge limits and roadbed strength. Before the convoy can cross a single kilometer, local crews reinforce weak sections of asphalt and install temporary steel plates over culverts. The permit dossier for a cross-province wind farm reads like a military operation. Every intersection, every turn radius, every hour of potential delay logged in advance. During a recent wind project in Inner Mongolia, the QAY 2000's journey took 3 weeks of staged transport, with support vehicles leapfrogging ahead to secure clear passage. The project manager describes the payoff: a single lift completed in under 6 hours that placed a nacelle the size of a locomotive atop a 150-meter tower. That speed wins contracts. In China's race to build the next generation of green energy, the ability to move 2,000 tons on demand is as much about national leverage as engineering prowess. Right now, each new crane redraws the boundaries of what can be built and where. As nations race to erect taller turbines and heavier infrastructure, the real contest isn't just mechanical. It's about who shapes tomorrow's energy grid. The next breakthrough could decide who builds the future. Stay curious.